Section 4.10, algorithms. So an algorithm is any step-by-step procedure. We use it a lot in mathematics. We also use it a lot in computer programming. So let's talk about certain languages. Again, pretty much any programming language is going to be based on an algorithm. And for a variable, for a computer, is slightly different because the way we change it is going to be different. But basically, on a computer, we are storing this value of c under this label of x. And do note that on a computer, unless we have a special type of value here, or a certain type of data, I should say, that can only hold one value. And most computer languages will have some sort of assignment statement. Here I've got this colon equals as a generic. Every computer language looks slightly different. So again, we're just going to use this as our general expression. And again, different computers are slightly different, but most codes are going to work pretty much the same order for the logic. So they go one after the order, and you can do a conditional to change that order if you need to. Again, each computer language looks slightly different. Sometimes you'll see an if, then else. Sometimes just an if, then. Again, the actual computer language will depend on which version is being used. We are also going to see do and undo, which generally go similar to an if, then. You'll notice we also have the else, because we want to say if the condition is false, what is the computer code supposed to do in that case? So let's say we've got this little bit of algorithm. What are we going to get after we do them? So let's start with A, and let's put in x equals 5. So if x is greater than 2, which it is, then y equals x plus 1. So that means y equals 6. If we then plug 2 into there, well, 2 is not greater than 2, so I'm going to go down into the else do and subtract from that, so x would be equal to 1, and then y is 3 times 1, so that is going to give me 3 for y. And we can have similar options for the second one. Here we've got a y value to begin with, and then we're going to put in the values, and we will get similar results, as you can see. We also have a while loop, and again, that is slightly different than an if-then loop, but it has some similarities as well. The word while marks the beginning, and if the condition is true, we go ahead and do it. If it's false, we just skip out of the loop. So these can sometimes be a little bit quicker and easier if that's what we want to do. So here is an example of a while loop. So we start with 1 and 0 for I and s. When we do it, we will then get s is 1 and I is 2. And at that point, we're going to hop back in because I is still less than or equal to 2. And we will then run our loop a second time. And we will end up with s is 3 and I is 3, at which point we are going to end. We can use something called a trace table to keep track of loops, particularly useful if we end up going through a loop more than one time. And you'll notice we list the iteration number. So before we do the loop, the first time through the loop, and then the second time through the loop, here's what we get out as our values. I'm going to not spend a whole lot of time with the for next. We don't see them very often, but you can see them here in the notes, which I'm going to scroll past. Let's look at notations for algorithms. Again, there's a number of different ways we can do these. A lot of it, again, depends on the programming language, but we are generally going to want to name, of course, all of our variables. We are generally going to name an algorithm. And of course, if you're going to do good coding, you'll want to put a comment in there that tells what exactly this algorithm does. We also want to, of course, list data type, because that might make a difference. And again, anything particularly unusual inside the algorithm in particular, we want to put comments. And of course, the output will have to have a name. And once again, we'll want to also note the data type if it matters. So let's look at an algorithm. Let's specifically look at the division algorithm. Now, if you've never seen this before, that's okay. We're just going to kind of hit the basics of it. So here, Q is the quotient, R is the remainder, A and D are basically what we're putting into this. So hopefully you can see down here, I've got a little while loop. So I'm going to start with R is A, Q is 0. So while R is greater than or equal to D, the thing that's being divided, R equals R minus D. So that remainder, I keep making it smaller. And then the quotient is going to be Q plus 1. And again, you can see we've got comments here to help describe what's going on as we go through that. So let's try it with the values of 19 and 4. So I put in 19 and 4 as my initial values. And again, those are my initial values for R and Q. The first time through, I'll get R is 15, Q is 1. I will then go into it again. Now R is 11, Q is 2. I go into it a third time, R is 7, Q is 3. And finally, I go into it with R is 3 and Q is 4. At this point, R is now less than D. That's why we finally stopped. And basically, I'm counting up how many times I go through it. And that's what gives me that Q value, the quotient. We could do something similar with the Euclidean algorithm. Basically, this is a way to find numbers that do multiply up to other numbers. So the greatest common divisor is certainly part of that. Here we're looking at two numbers. So remember, this is the largest number that goes into both of them. So the GCD of 72 and 63. Sometimes it helps to list the factors for each of them, but we can hopefully see that 9 does go into both of them. Let's look at the GCD of 10 to the 20th and 6 to the 30th. That's kind of hard to look at. So I'm going to look at 10 as 2 times 5 and 6 as 2 times 3. And you'll notice we do still have those exponents in there. So what is the largest thing in common there? And the largest thing in common is going to be 2 to the 20th. You can hopefully see that in both of them. And finally, the definition of greatest common divisor of G and G of 0 and 0 is not allowed. What's going on there? And there is no largest common factor that divides 0 and 0 because it works with everything. So that is why we do not look at that. We've got two little lemmas here for our Euclidean algorithm. If R is a positive integer, then the GCD of R and 0 is R. And if A and B are integers, not both 0, and if Q and R are integers such that we have our division algorithm, A equals BQ plus R, then the GCD of A and B is the same as the GCD of B and R. All right, we talked briefly about the Euclidean algorithm. Here is a quick description of that Euclidean algorithm. Again, that is the process where I'm finding that greatest common divisor. So if we've got 330 and 156, so my process, I start by dividing it. There's my quotient, there's my remainder. Here I am using that lemma that we just discussed. And I'm not low enough, so let's keep going. So now let's divide 156 by 18. Again, I've got my new quotient and my new remainder. So I can express 156 as 18 times 8 times 12. And my other number was 18, so we will have the same as 18 and 12. And again, I'm going to then continue that process so that my GCD is also the same as 12 and 6. And again, I do the process a fourth time, I'm sorry. The GCD of 12 and 6 is the same as for 6 and 0. And once we get that 0 in, we are pretty much good to go. because that is the other number, 6. So again, we said all of these GCDs are equivalent, and so I get my answer of 6. And once again, there is the Euclidean algorithm. This time it is written with a while loop. And if we wanted to do a trace table, we certainly can. These are the same numbers we saw earlier. So here is a full trace table where you can see here's the initial iteration 1, 2, 3, and then 4. And there's my final answer of my GCD. And that is everything in section 4.10.